Yeah, now comes the interesting topic. We have 3 points: heat engine, refrigerator, and heat pump. For today, we will focus on heat engine, and for the next lectures, we will come up with different definition or different ideas regarding the refrigerator and heat pump. So let's go to heat engine and we'll dig deeper here. We'll dig deeper. The thermal heat reservoir. It starts from what? We have a heat reservoir, as we said before, QH, right? So a part of environment which can extend heat energy with a system. It has sufficient large heat capacity and its temperature is not affected by the quantity of heat transferred to or from it. Its temperature is not affected by the quantity of heat transferred to or from it. Temperature remains constant in thermal reservoir. It remains constant. Process within it are quasi-static. So the reservoir which is at high temperature and supplies heat is known as heat source. So we have a reservoir and we call this heat source. Example are boiler furnace, combustion chamber, and nuclear reactor. We can take them like this. These sources, we call this one heat source. Heat source. And we have heat sink. The reservoir which at low temperature, that one was at high temperature, we call it heat source. But this one at low temperature and to which heat is transferred is called heat sink. We can say atmospheric air, ocean, or river. This one, heat sink. So let's see, what does heat engine mean then? A thermodynamic device used for continuous production of heat work from heat when operating in a cyclic process. I will repeat it. A thermodynamic device, this heat engine, used for continuous production of work from heat when operating in cyclic process. Both heat and work interactions takes place across operating devices. Both the heat and work interaction takes place across the operating. We have work, we have heat. From heat, we make some work. This is the concept of heat engine. So let's see this part. We have the heat source here. We have heat sink. So reception of heat Q1 from high temperature source at T1. So there is high temperature source at T1. So we are receiving high temperature through heat Q1, right? We have Q1 here. And there is partial conversion of heat received to mechanical work. So here we have heat, so partially is going to change this into work, mechanical work, right? And the other rejection of the remaining heat is Q2, which goes to the low temperature sink, which is heat sink at T2. So this is like repetitive process, which is cyclic or continuous operation. This is the characteristics of the heat engine. We have heat source, we have heat sink, and we have at the same time mechanical work, which is partially a conversion of the heat from the heat source, and the rest rejected heat goes to the heat sink at temperature T2. Let's see this statement, which one is Kelvin-Planck statement of second law of thermodynamics. So the Kelvin-Planck thermodynamics says, or also known as heat engine statement, states that it is impossible to devise a heat engine that takes heat from QH and converts all the energy into external work. So we couldn't convert this all energy into external work. This is not possible. Like there is always waste. So this is the statement of Kelvin-Planck statement. So we can say without losing heat, so colder reservoir. Always there is hot reservoir, there is QH, then heat engine. So this heat engine partially converts some of the heat into work and the other into cold reservoir. But this one is ideally, there is no process that converts the whole heat into work. This is the statement of this second law, Kelvin-Planck. So let's see how we measure the performance of emission. Like expressed as a ratio of what we want to and what we have to pay for. In the context of an engine, work is obtained at the expense of heat input, right? Accordingly, the performance of heat engine is given by net work output to the entire amount of heat supplied to the working medium. And this ratio is called thermal efficiency. Thermal efficiency is a measure of the degree of useful utilization of heat received in heat energy. Mostly we will see when we talk about performance, there is COP or coefficient of performance that we will see on the next slide. This is thermal efficiency, like the net work output over total heat supplied, and we have the work done, which is Q1 minus Q2. And if we want to know the efficiency, we have the net work output, which is Q1 minus Q2, but total heat supplied is from Q1, so we have Q1. So if we make it like this, Q1 over Q1 minus Q2 over Q1, we can cancel this one, then 1 minus Q2 over Q1. So this is like the thermal efficiency, and how we can get 100% of thermal efficiency. Is it possible? Is it possible? So the next one is heat engine, heat pump, and refrigerator. So we have heat engine here, we have the source, and we have Q1, and we have the device heat engine here. So it changes partially some of this into work and the other into the heat sink. And the other thing, like we have heat pump and refrigerator, we call them reversed heat engine. Let's say if we talk about heat pump, we have surrounding, which is T equal to atmosphere. So we take this temperature into this, and there's also an external work input W. So we have heat pump here, so we can generate the heat that we need or for space being heated. And if we say about refrigerator, we have here the space being cold with T is less than T atmosphere, and we have work input, we have refrigerator, so we emit this thing in surrounding and we get to equal to atmospheric temperature. The other thing is performance of a refrigerator and heat pump. The performance of a refrigerator and heat pump is expressed in terms of coefficient of performance, COP, which represent the ratio of desired effect work input. Most of the time this is a coefficient of performance, which is always desired effect over work input. So refrigerator and heat pump, let's say coefficient of refrigerator, which is heat extracted at low temperature over work input, right? This one was Q2, this one was work. We all know from energy conversion principle we have W is equal to Q1 minus Q2. So if you replace it here, Q1 minus Q2, and you have the heat extracted at low temperature Q2, this one for refrigerator, but for heat pump, the heat extracted at low temperature is Q1, so you will have Q1 over Q1 minus Q2. So this one is for today's lesson. I know it wasn't that much detail, but for the next 2 or 3 videos, it's gonna be more detail about this thing. So I want you to stay with me, and we will try to carry on in the way that we can. And I just want to say thank you for staying with me. I hope it was an interesting lesson, and stay safe and have a nice time.